Okay, so in alphabetical order, black is first. What is black? Unit normal, right? Unit normal. Blue,
That's the position.
that's just the original vector function, right? That's the, or it could be a position function, okay? Pink, binormal, and red, unit tangent. Okay, so this is now, here's your function. This is at pi over 2. We're going to find these at pi over 2 just for some more practice. And again, we don't want to go through and derive all the functions algebraically and then plug in pi over 2. We could do that, but it would take like 20 minutes, okay? So instead, we want to use the particular situation that we have. We know we're at pi over 2, so there's symmetry and there's assumptions we can make that make this easier. Okay, so where's my pen? Okay, so see how you do. This is at now t equals pi over 2. So can you find all 4 vectors? So position, unit tangent, unit normal, unit binormal. So any easy ones to start with here? So I'm going to move it around a little bit. Is there any real easy ones we can start with? Position. How do we get the position? Plug it in, right? It's just like a function. So at pi over 2, our position is pi over 2, 2, 0. Does it match with what we're looking at? Yep, we got an x-coordinate and a y-coordinate, and z is 0. It's in the xz plane. Looking good? Okay, cool. Now, the remaining 3, any that are easy, we can just write them down. The answer is yes. Can you see? One of those is really easy to see, and we can just...
It's just negative 1 in the negative y direction.
Which one are you talking about?
Sorry, the
Wow,
normal.
I'm all turned around here. Okay. Yeah. Sorry. There we go. Now we're back. So the black one, you think is?
It's just negative 1 in the y.
So
Or y direction.
because we're out here at the on the helix, we're out the very right edge of the helix. That vector is also going to be in the xy plane. Do you see that? So which one is that? Unit normal. It's what is it? 0. Negative 1. 0. Has a magnitude of 1 and it's pointing in the negative j direction. Are we good? So we're making that conclusion based on symmetry. We know we're at the far right side of this curve. And so right at that moment, it's the direction of turning is directly in the negative y direction. Okay, how about the remaining 2? Is there one that we can get? All right, so which of those 2, tangent or binormal, would be something that would be straightforward to get? Unit tangent. And where does that come from? Right, it's the unitized vector derivative function, right? That's all that the unit tangent is the vector derivative function, just then normalized, which means, or unitized, which means magnitude 1. So do that. R prime of t is 1, 2 cosine t, sine t, and we're at, right? So we're at pi halves, so r prime of pi halves is 1, comma, 0, 1. Is that the unit tangent vector? No, because that has length something greater than 1. So then we just need to make that a unit vector, and that's our unit tangent vector, which is that 1 over radical 2? It's okay to have radicals in the denominator?
Yeah.
Sure. It just, back when you were doing algebra and you weren't talking about meanings, that you just needed something else to do, right? It just said, we better do this because we better do it. We better rationalize the denominator. But there's nothing wrong with having square roots in the denominator. Trust me, it's fine. It's still the same value. Okay, and then it saves us time to talk about more interesting things. Okay, so now what about the unit binormal? Okay, you could cross product. You could definitely cross product, but again, we could use some intuition here. All right, so what about the plane that it's in? So what's one thing we can say about the unit binormal? Parallel to xz, therefore, y is 0. So just like the unit tangent, its y component is 0. And remember, those two have to have a dot product of 0, and we can use that fact to figure this out quickly rather than working through the cross product. We can work through the cross product, that's perfectly fine. But look, we got, so positive x direction is to, let me get to the right. I'm going to turn around this way. So positive x is to the right, and z is up. And what do we have for unit tangent? Was 1 over radical 2 positive, and then 0, and then 1 over radical 2 positive. And now we need a vector whose dot product with that is 0. So, for which?
For the y.
We're in x and z, right? This is x and z. So, x component is?
Oh wait, sorry. Well, 1 over.
It also is forward, in the positive x direction, 1 over radical 2. And then z component? See how much easier that is than the cross product? Okay, now this problem is rigged, right? Pi over 2 is a very nice point. It's a very nice point on the curve. And so it turns out to be rigged. But I'm just, look for situations where you can, make deductive, use deductive reasoning rather than just always computing out formulas, right? So questions on that? All right, cool stuff. So then we want to talk about something called curvature. So I want you to look at this curve. Any questions? Last chance. So, hold on. So what do you notice about the sides of this curve, meaning greatest y and least y, versus the top and bottom, greatest z and least z, when it comes to the curve with the ellipses? So how does this curve compare to this up here? So you see that this is like more curved than the top is more straight. You see that? So that's very low-tech language, but this just curves more. It's a tighter curve, and this is more straight up here. So this is the idea of curvature of a curve. How curved is your curve, right? Is it closer to being straight or closer to having a tight curve? So that's what we're going to talk about next. So curvature is defined as the rate of change of direction with respect to arc length. So let's think about that. Does that make sense? So for a given distance along the curve, how much does the direction change per distance along the curve? Does that then compute how curved it is, right? So for the same change in arc length, Do you have a lot of change in direction or just a little change in direction? So then what would that be? That would be, what's our direction? So how do we mathematize direction?
Just the position.
So the change, so no, it wouldn't be position. It would be change in, thinking of T, N, or B. So change of direction would be change in T with respect to arc length, which would be S. So S is arc length. So this is Greek kappa. So this is a function, right? The curvature is going to depend on where you are on the function, just like I showed you on the helix. At pi over 2, the curvature was a lot higher than, say, at pi, where it was flat. So it's going to be a function of t, and it's going to be the rate of change of the unit tangent with respect to how much a change in arc length. Okay? So this is kind of the theoretical formula behind curvature, but this is not how we'll calculate curvature. Okay, so another way to think of this is, so the change in unit tangent is t prime. And the change in arc length, a little change in arc length would be the magnitude, so yeah, so these both magnitude of t prime over magnitude of r prime. Because remember, r prime gave us how much curve was swept out per t, right? And so that's like arc length. We take the magnitude of that, and the magnitude of t prime would be how much t changes. So so if you said n, so this is like n, right? This is kind of like n.
Wait, why is R prime the R3?
Because remember that the rate of change of the vector function told us how much arc you got for a change in t. Remember that? So that's like arc length, right? Make sense? Yeah. So whose direction was in the direction of the curve, and the magnitude of that was like how much arc length per t. So that's why it's arc length. Okay, so this is the kind of the theoretical side to it, but when we calculate it, we're going to calculate it with r prime and r double prime. So would that be a matter of dot product or cross product? So could you know this at this point? Let's see. So so why are you saying dot?
Because we use dot to project vectors onto vectors. So
Right.
I'm thinking it'll be useful for curvatures.
I don't know if you can know this at this point. It's cross product. So this is a formula that we'll actually use to calculate curvature. So it's going to be the first derivative of the vector function cross the second derivative, the magnitude of that, divided by the magnitude of the first derivative cubed. As we talk about acceleration, this cross product will make more sense. But so we'll kind of come back to why this is cross product. So given an R3 vector function, this is the formula you're going to use to calculate a curvature function. This curvature function. So in R2, there's a simpler version. If you just have a function of x, y equals f of x, then it's this function. I'm not going to take the time to derive these. I'd rather talk about curvature and show you some cool animations. So in R3, this is kind of the most generic formula to calculate it. In R2, if you have y as a function of x, this is much easier to calculate this way. And I think in the web work, they even show you a third formula. And so they're going to ask you to calculate curvature by a third formula. So you just follow the symbols correctly, right? So just as long as you know what every single individual thing means, and how it's represented, you can do the math, okay? It's cross product, magnitudes, division, cubing, it's all things you can do. All right, so let's find the curvature of a circle with radius A. So I want to do this. I want to use R3. So what's the simplest parameterization or vector function? The simplest vector function we have for a circle with radius A. I'm going to start off with that. Okay, so he wants A cosine t, and if we're in R3, is this a circle with radius A in R3? Is it? Is it the simplest one you can think of? Well done, right? That's good, right? So that's the circle of radius A, center 0, 0, in the xy plane. All right, now we want to find the curvature of that. So which formula are we going to use? Exhibit A or Exhibit B? A, right? So this is for if you're in R2 and you have y as a function of x. So this won't work. See that? Well, and we're also in R3. This is in R2. Right? So we're going to use this. So what does that mean we need? We need the first derivative vector function, the second derivative, we're going to take the cross product, and take the magnitude, and then take the magnitude of the first and cube it. But there's some nice things are going to happen when we go through that process. So I'm going to go a little bit fast here for time's sake. So what's our first derivative? And I'm going to use my s's and c's instead of sine and cosine, and then a cosine t. Second derivative. Just the derivative of that. Okay, thank you. You're right. Okay, now cross product. So cross product means, I'm glad I wrote those on top of each other so I don't have to rewrite it here. I, j, k. So the cross product's going to be, for the I component, we can get 0. I think we can get 0 for the I component. Is that right? Going this way, 0, 0. That's nice. This is J component. 0 going down this way, 0 going this way. That's nice. Finally, Z component is going to be negative A sine squared t. And then going down this way, negative A cosine squared t. Did I do the math right? For the cross product? Okay, so what is the magnitude of that? So this formula is calling for the magnitude of the cross product. So what is minus A sine squared minus A cosine squared? That all becomes... So, okay, so... oh, it's plus this way, right? Plus this way, and then... Oh, geez, I got them both wrong. Plus and plus, right? So going down to the right, minus times a minus is a plus. Going down to the left... I think I went down to the left first. That was the problem. So down to the left, minus and a minus makes plus. Okay, so 0, 0, this becomes? Actually, these are a squareds, right? So then factor out a squared. Sine squared plus cosine squared is 1. And so I think that's the cross product. Is it right? After the corrections, did we get it right? Therefore, the magnitude of that is a squared. Numerator. We got the numerator, right? Denominator is the magnitude of r prime cubed. So I'm going to take the magnitude of this and cube it. What is the magnitude of that vector function? So yeah, we could do the math, or we could say, what is that? That's just another circle in the xy plane, right? With radius what? A. So isn't the magnitude of every vector there A also? And if you do the math, you do square root of that squared plus that squared, you're going to get square root of A squared or A. So the magnitude of r prime is A. And so therefore the curvature is? No. A squared over A cubed equals? Okay, so now, a very, very important result. The curvature, and what was A again? Radius. Why does it make sense that curvature is 1 over the radius of the circle? That should make sense. If we understand what the radius is and we understand what the curvature is, that relationship should make perfect sense. Can anyone explain that? Yeah, Aiden.
The circle has to turn faster the smaller the radius is.
Okay.
So it makes sense that it would be inversely proportional.
Okay, yeah, so if you got a small radius, do you have high curvature or low curvature? Super high, right? Like a super small circle is very, very high curvature. And so with a small radius, you're going to get a big number if it's 1 over a small number, right? And if you have a circle with a huge radius, low or high curvature? Very low, right? This has, you know what particle accelerator is? So they do, nuclear physics and testing and all kinds of crazy stuff by like accelerating particles and crashing them into each other. So they want it to be they want to get a lot of speed, but they want them to crash in a straight line, right? So these particle accelerators are gigantic circles, right? They're these huge circular tunnels where they send the particles around in circles. But they want them to come in as straight of a line as possible. So that's why they build these huge circles. Low curvature, right? Low, straight. So that means a really big radius. Really big radius. Okay? So, then we get this thing called so we're looking at this graph right here. Oops. So this is the graph of this right here. Come on. Gee whiz. This is the graph of 1/6 x cubed minus x squared. So where is the curvature high? Where is their high curvature? 0 and 4. You see that's the highest curvature. And where's the curvature the lowest? There's actually one place where the curvature is 0. See where that is?
That line over there?
No, forget about the line. Just ignore the line. At 2, at the inflection point, right? At the inflection point, so it's going from curving one way to curving the other. There's a moment of straightness there. That's what an inflection point is. It's a moment of linearity. So you have 0 curvature right there. Okay? So we talked about how the curvature is inversely proportional to a circle. So at any point on a curve, if you take a really, really small piece of that curve, really small piece, there's a corresponding circle to that. So a small enough piece of a curve gives us a single value of curvature. And so then there's a circle that has that same curvature based on 1 over the curvature is the radius, right? And so then that's called the osculating circle. So at any given point, any given moment of the curve, there's a circle that has the same curvature at that moment as the curve. This is called the osculating circle. So when is the circle the smallest? When the Curvature is the greatest at the max and the local max and min there. And then when is the curvature the least? For great, high, x, and so I'm gonna watch for a second. It'll disappear for a second. Ready? Gone. Or it just ends up being a straight line, right? So it has an infinite circle with infinite radius, which is just a straight line. So that little bit of the curve that we match to a circle, then the circle has a plane, right? So that circle is a plane. That's like the plane the curve is in, and that's what we called the osculating plane. So the osculating circle is an osculating plane. It's the plane that the curve is in at that moment. And then the curvature of the curve is the same as the curvature of the osculating circle is the same as the curvature of the curve at that whatever that x value is. Okay, so now you think this is cool. Now I got something really cool to show you. I'm just gonna find it. You ready? So here's a curve, vector function. So slightly complicated based on sines and cosines. So here's the TNB frame. We've seen this before, but this is for these three. So we got the unit tangent, always points the direction of the curve, unit normal, exactly what we said. Binormal is perpendicular to both the tangent and normal vectors. So you determine, maybe they've already given us the colors. So we're going to look at, as it moves along. So which is which? Red is what? Unit tangent. Blue is? Which is blue? Normal or binormal?
Binormal.
I think blue is binormal, right? Green is the normal vector. Okay? So now they're going to add the osculating circle, right? That'll be in the plane of which two vectors? T and N. And its size will be based on the amount of curvature. So when it's large, then the curvature is low, and when it's small, the curvature is high.
Does the binormal vector essentially point in the direction the circle is
It's orthogonal to that plane. The binormal is orthogonal to the osculating plane. Okay, so now we're gonna hold the T and B frame constant, and we're just gonna look right down T at all times. So this is just T is we're heading forward, right? This is so the circle is always up, and so your binormal vector is that way, and your normal vector is the green one pointing up. Let's see that last one again. Slow it down a little bit. Oh, jeez. Okay, so you understand what you're looking at? So now the three-dimensional coordinate system is now it's moving along the curve, but now we're in the frame of reference of that coordinate system, just holding that steady, and then letting the curve change according to that. All right. So let's do a problem here, something a little easier. So does the idea of the oscillating circle make sense? It's basically if you take a little piece of the curve, teeny little piece of the curve that has constant curvature, it's matching the circle with the same curvature at that point on the curve. Okay, so let's change the function to x squared. And here's the osculating circle. So then I wanna say for x equals 1. So here's the osculating circle for x equals 1. I want to find the equation of that circle for when x equals 1. You guys are going to help me figure it out. I have no idea how to do it. I'm just kidding. I know how to do it. But you guys are going to help me figure it out. So how are we going to find the equation of that circle? What's that? All right, so he wants to find the curvature using the R2 formula. Why is that going to help us? What is the curvature going to help us? Yeah, then 1 over that will be the radius. So we'll do that first, sure. All right, so what's our formula for curvature? Anyone write it down? Magnitude of f double prime of x. Is this it?
Yeah.
Okay, very cool. All right, and what's our function? X squared. Second derivative is 2. Magnitude is? So for y equals x squared, we're going to get 2 over 1 plus, first derivative squared is 4x squared to the 3 halves. Okay, and so we want at x equals, so that's the function, right? This would give the curvature at any point on the parabola. It's a function of x, right? As x changes, your curvature changes according to this function. But we're interested in x equals 1, right? We're interested in x equals 1. At x equals 1, our curvature is 2 over 1 plus 4 to the 3 halves. So 2 over 5 to the 3 halves, which is root 125? Or 5, is that 5 root 5? Is that 2 over 5 root 5? We good? Therefore, radius equals 5 rad 5 over 2, 1 over the curvature. Okay, we got the radius of our circle. What do we need next? Center. So we have all the tools, just we got to figure it out. How are we going to find the center of the circle? Aiden has an idea. Anybody else? Alexandria. Okay.
It's on the circle.
Good.
And then you know that the radius is 5 root 5 over 2.
Okay.
So that's like the distance to the center.
Okay. So we've got this point, and then we can use the radius 5 root 5 to the center. So 5 root 5, where's that going to put us? So what's missing there? So everything you said was correct, but you just got something's missing. Yeah, Jeffrey.
We need to find the line, the direction that's orthogonal to the tangent line.
Good. Okay, so we need to find anything like that we've been learning lately?
The normal vector.
He wants the normal vector. Is the normal vector point in that direction? Normal to the curve, right? Normal to the curve. So if we have the normal vector, then what could we do? We're at the point 1, 1. What's that?
Multiply it by the radius to get the vector and then do vector addition.
Good. Right. So do you see that we're going to go a distance of this along that direction? That's just basic vector stuff, right? We can do that, right? So, right?
Sure.
Don't you remember? find a vector that has magnitude such and such in the direction of this vector. Remember doing that? Yeah.
Yeah.
That was a problem that we saw for test 1 stuff. Find a vector. So really, if there's a vector that extends from 1, 1 to the center, right? If we had that vector, we'd be home free. Now we have the direction of that vector, and we have the magnitude of that vector. So we can find that vector, right? So now we just got to get the direction. So what is that direction? So let's we can use some of our, heuristics that we've been learning, right? So I showed you a heuristical. You know what heuristics are?
Nope.
Ways of solving a problem, right? And it's often like an efficient kind of, convenient way of solving a problem. And I showed you some heuristics about doing this. Were you going to say something?
Well, we can find the slope of the tangent line.
Okay.
And then take the inverse of it, which would give us the slope perpendicular.
Okay. So having a slope there, all right, that's good. So what is that? So
the slope is 2x times, and then you plug in 1 for x.
right?
So 2.
2.
And then the inverse would be -1/2.
Therefore, the slope of this one is
-1.
-1/2. Or what else could we draw here that we've learned?
The unit tangent.
What is the unit tangent vector then? If the slope is 2, what would the unit tangent vector be? So the unit tangent at x equals 1,
2, 3.
the slope is 2. What does that mean?
Up 2 over 1.
Okay. So it would be?
1, 2.
Is it 1, 2? Is that the unit tangent?
Wait, no, you have to divide by the magnitude.
Right, so we want the unit vector. 1, 2 is the right direction, whoever said 1, 2. We want
1 over square root 3, 2 over square root 3.
5.
Oh. Oh, yeah.
So if the rate of change, if slope is 2, rate of change is 2, that means that y is changing 2 for every 1 in x, right? So that's the direction of 1, 2. Unitize it, and that's our unit normal, and then our unit tangent. So then what's our unit normal? Looking at the picture, here's the heuristical method that I was showing you. So the x component, positive or negative? Negative magnitude. So now if it's perpendicular, this is what? 2 in x for every 1 in y. Therefore, -2 over radical 5 and positive 1 over radical 5 because it's over 2 and up 1 now, but over to the left. Dot product 0? The dot product of those two needs to be 0, right? Orthogonal. It is. Okay, I think we're getting close, right? So we've got the unit normal, and that's the direction that's pointing right at the center. We've got the distance we need to go. So what is the coordinates of the center? I think we can just write it down now. We've got the starting point 1, 1. We've got the vector -2 radical 5, 1 radical 5, and the distance we need to go. So coordinates of the center. It's going to be a little ugly, but so starting point is 1, and then we're going to add what? 2 rad 5 times this, right? So we want this. This is already unit vector, so if we just multiply it by the radius, is that just -5?
Yeah.
Okay, so 1 plus -5. I just remember the coordinates in the center being a little uglier than that. Okay, what about the y coordinate? So 1 plus 5 halves. Therefore, our center is -4 and 7.5. Does that look like it could be right? -4, 7 halves is almost 8, right? Look like it'd be right about there? Okay, so let's, I'm currently sketching the oscillating circle according to my function, but let's just graph that circle, the circle we came up with statically, and what should happen? Same. So, what's the equation of our circle? X plus 4. Quantity squared. Center -4, right? Plus y minus 7/2. Quantity squared equals
5√5/2 squared.
Is that 4 over 125 then? If I square that? Can I just do 4 over 125?
It would be 5
Oh, what was that? Oh no, that's not right. It'd be 125 over 4, right?
Yeah.
But I'll just do it this way, just so there's no question what we're doing. All right, the moment of truth. When I turn the graph on, what should I see?
Same circle.
There shouldn't be two circles, right? The circle I was showing before this new one should overlap perfectly with it. So blue plus red equals
Purple.
indigo. Not purple, it's indigo. Just kidding. See that? So off. So this is that was the true one, and this is the one we found. Right on top. Okay, any questions on what we did? Did you follow all this? Follow all the logic? Okay. Pretty cool. So let's talk about, so that's curvature and osculating circle. Any questions? Let's talk a little bit about acceleration. Oh, no, before we do that.
What are some applications of curvature? Like using a circle.
What's that?
What are some of the applications that you could do with a circle like that?
Oscillating circle? I don't know. Something, I'm sure there's stuff in physics that uses that. Yeah. Yeah, like aerospace stuff. Okay, remember this is my favorite function here.
Does this function describe anything cool, or is it just a cool looking function?
What's that?
Is this like describing something really
It's just
cool
cool.
we'll find out later, or is this just your...
No, it's just cosine t and this quartic and the sine t. This is it. So it's just maybe by some slim chance it represents something in the real world, but not that I know of. That would be quite a coincidence. Okay, so I want you. So we've been talking. We're going to talk lots of different kinds of functions in this class, and so those functions that we talk about can be broken up into two kinds of functions: real valued functions and vector functions. So when I say real valued or vector, is that referring to the independent variable of the function or the dependent variable function? So meaning real valued, vector valued, the real or the vector, is that referring to independent or dependent? Dependent, right? We know with vector valued functions, the vectors are what comes out, right? For a given value of t, we get values of vectors. So a real value or scalar function then is when the result of your function, what it gives, what it outputs, is a real value, versus a vector function, it's going to output vectors. So go through each of these 5 and determine if it's real valued or a vector function. And then we want to write a mathematical representation of it, right? So if this function is r, if this is the r function, then in terms of r, what would the speed function, the velocity function, direction, etc. So what is it, real valued or vector function? And then what? How would you write it mathematically in terms of R? Go. You got a couple minutes. And you can.
Distance per unit of time.
No, it's the magnitude of the derivative function. That's the speed, right? And so what's the velocity? Just the derivative, right? Velocity is just the derivative. Speed would be just the magnitude, and then that gives you a scalar function, a real valued function. Direction of motion function. Direction of motion function. What would that be? That's a vector function, right? And which function is it? Unit tangent function, right? Direction of turning function. Vector function. And what is it? That's the normal. And remember where this came from. This was that thing normalized, right? And then this was the derivative of the unit tangent normalized. Acceleration function. Vector function, and it is? Second derivative. And that's what we'll talk about Monday. We'll start talking about the acceleration function on Monday.